Okay, so we are recording this session. This is the first session for week 5, and tonight we're going to talk about two-sample hypothesis testing. So until last week, we were discussing one-sample hypothesis testing, and if you remember, we had discussed um, testing for proportions and the mean, right? And only one population and one sample was involved. Well, tonight we're going to take that concept and then apply it to two-sample hypothesis testing where you're comparing the samples against each other. Okay, so essentially what you're doing is you're comparing the two populations against each other. So for example, if we're if we have two populations and we want to compare um, their proportions, then we take a sample from each of the two populations, calculate the sample proportion, and then compare them against each other and do a hypothesis test, just like last week. Tonight should go much smoother because the concept is the same. You'll have a test statistic, you'll have a p-value, everything will be the same. The only difference is that the equations, are different. But the nice thing again is if you were to use StatCrunch, then it's essentially exactly the same as last week. Okay, so I'm going to share my screen and then we'll get started. So if you can just confirm that you can see my screen here. Okay. It looks like we have about 40 students tonight. Great. Okay, so, oh yeah, sure. I can make it bigger. Is this better? Okay, great. All right, so let's get started. I do want to remind you all that the second session is going to be tomorrow. So it's not on Thursday since Thursday is Thanksgiving. So we will host the second session tomorrow at 9 p.m. Eastern Time. Okay, so here's the first problem. And in this problem, you have to, well, first of all, this problem involves two samples. Okay. Um, well, let's talk about it, and then maybe I can expand on, you know, what is being considered here. So determine whether the sampling is dependent or independent, indicate whether response variable is qualitative or quantitative. So there are four things here that are important. Dependent sampling, independent sampling, qualitative variable, and quantitative variable. Now, I think this is easier to explain first. Qualitative variable is simply a variable that sort of classifies an individual. Okay, so and we'll discuss the example given in this problem as being qualitative or quantitative. But qualitative, essentially what you do is you're classifying a unit or an individual. Quantitative variable is a variable that is numerical in nature. Okay, so like a number. Okay, so something you can measure, something you can calculate, that's quantitative. Qualitative you can't. Okay, so let's let's read this problem now. And the independent and dependent sampling. I think this will be best explained once we go through this example and then see which option is correct. Okay, so a researcher wishes to compare personality types of patients with and without um, narcolepsy. She obtains a random sample of 706 patients of each category who take a personality inventory and determines each patient's personality types. Okay, so what's going on is so there's a random sample of 706 patients of each category who take a personality inventory and determines patient's personality type. Okay, so essentially what's happening is you're taking a sample, of 706 patients and you're trying to assign personality types, okay, to each patient. So, and as you know, the two personality is a binary um, binary assignment. Okay, with or without, right? That's yes or no kind of assignment. So what do you think? What do you think? Say if I have a sample size of 700 patients, I take each patient and I check their personality type. Okay, and imagine it's a 0 or 1 kind of a thing. Okay, I put them either as 0 or a 1. Do you think this is a dependent sampling, or do you think this is an independent sampling? And then we'll expand on why we think it is dependent or independent. It's independent. Very good. Yeah, because why do you think it's independent? Conrad, that's good try. A little bit more than that. Very good, Aaron. That is correct. That is absolutely correct. So here's the answer. Say I select the first person, yeah, okay, the first patient out of the 706 patients, and I assign them to, say group one, okay? So there are two groups. I assign that first person to group one. Now I take the second patient. Now, and you can appreciate that the assignment of the first patient will have absolutely no consequences on the assignment of this second patient, okay? The second patient will be assigned independently of the first patient, okay? Because I'm only interested in studying the second patient's personality type, not on, it's not dependent on the first one. This is the reason why this sampling method, putting them into one group or the other, is independent, okay? Is this clear? I hope this is clear. Independent versus dependent. And we'll do a few problems later where we will consider dependent sampling, and I'll tell you what that is. Okay, great. Now, is this variable qualitative or quantitative? What do you think? Is this quantitative or is it qualitative? Remember, qualitative variable classifies an individual. Quantitative variable is a variable that is numerical. You can put a number to it. So which one do you think is this? It's a classification. Very good. So it is qualitative, right? It's essentially you're trying to, you know, there are only two kind of personality types considered here, and it's either a yes or a no. You cannot put a number to this, right? So this is qualitative. Very good. Okay, so I think this was a fairly straightforward question. The second is very much the same. So you have an educator who wants to determine whether a new curriculum significantly improves standardized test scores for students. She randomly divides 60 students into two groups. Okay, so 60 students are divided into two groups. Group 1 is taught with traditional curriculum. Group 2 is taught using the new curriculum. So at the end of the school year, both groups are given standardized test. Okay, so essentially what they're doing is there are two groups. One is taught the same way as, as the current curriculum. The other is taught with the new curriculum. And then you test the two groups at the end to see, is there a difference? Yeah, it's like a control and test experiment. So you have to determine whether the sampling is dependent or independent. Okay, now you gotta stop here and think about this. Initially, she is randomly dividing 60 students into two groups. Do you think it matters? Do you think the group student assignment to each of these two groups matter? As in, are they connected somehow? Or is it completely random? And if it's completely random, do you think it's dependent or independent? It's random, yes. So do you think it's independent? Yes, it's completely independent of each other. Assignment of one student to one group does not dictate, who gets assigned to the second group. It is absolutely independent. Okay, so this is again an independent sampling method. And okay, so now what we are doing is we are measuring for the two groups. We're measuring the mean scores for the standardized test. So do you think this response variable is qualitative or quantitative? Okay, very good. It is quantitative because now we're talking about the mean score. Score will get a number, right? It will have a number assigned to it. And therefore, it is going to be quantitative. Excellent. So is this clear? Okay, and this is really um, all that is to dependent and independent sampling and qualitative and quantitative variable. Yes, we will consider a dependent sample. Actually, let me give you an example right now. Imagine that you wanted to do a hypothesis test of, say you were hypothesizing, you think that um, sons on average are taller than their fathers. Okay, so that's your hypothesis. And say that in order to test this hypothesis, you go out and you get a sample. Okay, you get two samples, one for fathers and one for sons, and you have to sort of do the hypothesis test. Now, in this example, do you think this example should be dependent or independent? Can I just go out, get a random set of fathers, and then go out, get a random set of sons? Or do you think it's better if I go out to a household where there's a father and a son, so that if the father gets selected in the sample, then the son also gets selected in the other sample? Do you think this is better, or do you think it's just randomly assignment is better? Yeah, this would need to be dependent, right? Because it's better in order to do this test, in order to do this hypothesis test, you must have a connection between the father and the son, right? You cannot have a random set of fathers and a random set of sons because, they may not be sort of connected genetically with each other, right? But what you want is you have to go to a household, select the father, and if the father is selected in sample one, then the son must be selected in sample two. And then you can do this hypothesis test. Okay, this is an example of a dependent sample. Uh, Selection of sons depend on selection of fathers in the sample. Okay, does this make sense? Okay, awesome. Okay, I see there are a lot of comments. I'm hoping these are comments and I didn't miss any questions. Just to remind you, if there are any questions that maybe one of you can answer, go ahead and type the answer. And then obviously I'll keep looking as well. If there are any questions that need my attention, I will answer those. Okay. Now we're gonna switch to hypothesis testing. So let me start off with this problem. So here it says conduct a test at alpha 10% level of significance. First, you have to determine the null and the alternative hypothesis. You have to calculate the test statistic. You have to calculate the p-value and assume the samples were obtained independently of, well, the assumption here is the samples were obtained independently from a large population. Here is what they're actually telling you what the alternative hypothesis should be. Okay. And the sample data is given here. So here's what's happening. Okay. So let me now tell you what is going on here. Okay. So let me make this a little bigger here. So what you have is you have these two populations. Okay. This is population 1. This is population 2. Okay. So there are two populations, And obviously there are um, some proportion that you're testing, okay? That proportion here is called P1 and here is called P2, okay? This is proportion 1 and proportion 2, and you want to test them. You want to test whether the null hypothesis is that P1 equals P2, or the alternative is that P1 is not equal to P2, or perhaps P1 is greater than P2, or perhaps P1 is less than P2, okay? So this is it. This is really the heart of this hypothesis test. So remember last week we were testing whether this proportion is equal to some value. Remember that? And then the alternative was that it's not equal to some value, that value, or is greater than that value, or less than that value. This time we're just testing proportions against each other. This is the only difference, okay? Can't hear. Alfred, can you hear me now? I'm hoping you can hear me. Can anyone? I'm hoping everyone else is hearing me, so this might be okay. Okay. Seems like Alfred might have to perhaps check his speakers or log out and log back in. Okay, so this is essentially the hypothesis test. So what do you do? So what you do is you go ahead and you take a sample, a small sample. Okay, so I'm gonna call this this is a sample, and this gives you P1 hat, right? And you take a sample here, okay? And then this gives you P2 hat. And then all you have to do is, okay, this is pretty important, so see if you can follow this. So you take the two samples, you calculate the two proportions, and then all you have to do is compare these proportions using a test statistic, okay? So remember the test statistic last week, there were two equations, one for the proportion and the um, one for the mean. Now the equations will be different. So in this case, for example, here is the equation. Now don't get scared, okay? It's a little bit tedious, but let's figure it out. The equation is you have P1 hat, you subtract the P1 hat, and then P2 hat, okay, this way, and then you divide it by this long thing, okay? P hat, there's no number here. I'll tell you what this is. So I'll tell you in a minute what that is. Okay. And so this is the equation. And P hat, this P hat, where there is no number associated with it, is essentially just so let me tell you what this is. So when you take the first sample from population 1, you get X1 and N1, right? X1 is how many individuals in the sample have the characteristic you're interested in. And remember that P1 hat is simply just X1 divided by N1, right? And then here you have X2 and N2, and then P2 hat is simply just X2 divided by N2, okay? Now all you have to do is set up this equation here, which will give you the test statistic. P1 hat minus P2 hat, you will have it from here, divided by this whole thing. P hat is equal to X1 plus X2 divided by N1 plus N2, and then the rest of this is here. Okay, so this is simply the test statistic when you are comparing two proportions. Okay. Yes, we can, but again, if you do it blindly in StatCrunch, then you don't really know what's happening in the background, right? And I think it's important as statisticians to know how StatCrunch actually does this. What is it doing? Like, how is it actually calculating the test statistic? And what does it mean, right? That's also very important. So, it's the easiest thing to remember here is that, um, well, it's not really there's really nothing easy to remember here, but the one thing to remember here is last week we were, considering this P1 hat minus some value. Well, this time, instead of the value, we have the second proportion. And then the rest of the equation is set up this way. Okay. This is the equation for test statistic Z, which is the test statistic for proportions. Okay. It's a two sample test statistic for proportions. Okay, so this is the equation to remember. Now, let's look at this problem. So the data has been given. X1 is 123, N1 is 247, X2 is 131, and 2 is 311. So let me now walk you through this. X1 is given, N1 is given, X2 is given, N2 is given. Now, do you agree that since I have these four, I can calculate P1 hat, I can calculate P2 hat? Do you agree with that? Okay, very good. So I can calculate that using this equation, right? It's just x divided by n. Do you also agree that I can calculate my p hat? All I have to do is sum the x's and then sum the n's. And then using this equation, I can calculate p hat. Do you agree with that? Right? It's very simple. Okay. So now do you agree that I have p1 hat, I have p2 hat, I have p hat, I have this, I also have n1, I have n2. So do you agree I have everything here? I can easily calculate my test statistic, can't I? Right? So I have everything I need to calculate the test statistic Z using this equation. And it should be a very simple plug and play kind of calculation. But now let me show you how you can do this in StatCrunch, and StatCrunch is going to essentially do this. Okay. If I can put the numbers. Okay, so I mean, I wasn't planning on doing this manually because that would take quite a bit of time, but here. So this is 123, right? 247. So I'm essentially just copying it from here. 131 and 311, right? So I have everything here. So I mean the rest I'm hoping you can just simply calculate it, right? This is just 123 over 347 or 247. This is just 131 over 311, right? And then this is just 123 plus 131 divided by 247 plus 311. Okay, so all I want to make sure here is that you appreciate that we have everything here. Everything has been given. We can calculate this manually. Okay, we don't have to do it manually, but we can calculate it. And this is what StatCrunch is going to do in the background. Now, if we go back now to StatCrunch, let me open this in StatCrunch. And so if you remember, for proportions, we used stat, proportion stats, and we used one sample last week. But did you notice that we also have a two sample option? So we're going to go to two sample this time because we have two samples. And I'm going to again go to summary with summary. Okay. And notice that they have given you the boxes for two samples. And all you have to do really is just place these numbers in the correct boxes. So for sample one, number of successes is 123 out of 247. And for sample two is 131 out of 311. Okay. And what is the alternative hypothesis here? Alternative hypothesis, they want you to use P1 is greater than P2. So make sure to change that And by the way, they have given it differently. Let me show you what this means. Okay, probably should have talked about this before, but let me show you what that means. So I'm going to use the space here to show you what that means. So when I say under the null hypothesis that P1 equals P2, that's the same as saying P1 minus P2 equals 0, right? Because I can bring this P2 here on the left side of the equation, and I'll be left with 0 here. But when I bring this P2 on the left side, this will be negative, right? So P1 minus P2 equals 0. These two are the same things, okay? So the null hypothesis can also be written as P1 minus P2 equals 0. Alternative, say if this is the alternative hypothesis, P1 is not equal to P2, well, that's the same thing as saying P1 minus P2 is not equal to 0. If it's P1 greater than P2, that's the same as saying P1 minus P2 is greater than 0. P1 less than P2, same thing as saying P1 minus P2 is less than 0. Okay, so it's just a matter of bringing this P2 on the same side as P1, and then you get, these set of equations. The thing is that StatCrunch will give you this set instead of this set. Okay, that's why you see here it says P1 minus P2 equals something, right? So under the null hypothesis, because P1 equals P2, so this value will be 0. And then under the alternative hypothesis, remember we said we want to test P1 is greater than P2. So I will just change this to greater sign. The easy way to remember this is that whatever sign you see in the problem is the sign you have to put here. Okay. And that's all you have to do. You plugged in the numbers, selected the correct hypothesis, click it, and take a look at this. This Z-stat is essentially what is this whole equation here. Okay, so what it did was it took your numbers, it plugged them in, calculated all these, and then calculated the Z-stat, which is this 1.808. Okay, and then the associated p-value with that Z statistic is given right here, 0.0353. Okay, so is this, first of all, is this clear how it calculated the Z-stat? I mean, I'm hoping that you guys now will appreciate that it makes this so easy to calculate this, right? But if I didn't show you what it's doing, then you would kind of, you would take it for granted, right? That it's easy to calculate. Well, it's kind of not easy to calculate. It actually makes it very easy for you, but it does involve a lot of computations in the background, right? So, okay, so let's see. So choose the correct null and alternative hypothesis. So we did that. Determine the test statistic. Well, the test statistic is here, 1.81. That's up to 2 decimal places. Determine the p-value. Well, the p-value is here, 0.0353, 0.035. That's up to 3 decimal places. And then they're asking you what is the result of this hypothesis test. So if my alpha is 10% and my p-value is 3.5%, what is the conclusion? Brian says reject. That is correct. P-value is less than alpha, right? 3% is less than 10, 3.5% is less than 10%. P-value is less than alpha, so you reject the null hypothesis. So you reject the null hypothesis in favor of the alternative hypothesis, okay? Can I explain the A answer? Well, the A answer is simply just the alternative hypothesis is always that P1 equals P2. That is always the case. That's always what we're testing. The alternative is given in the problem. The alternatives, they want you to test P1 is greater than P2. Okay, so that's why the alternative hypothesis is that P1 is greater than P2. Okay, alpha does not equal P1. Alpha is 10% here, right? It says alpha equals 10%, and it changes from problem to problem. So when we got our p-value, this is just like last week. When we got our p-value, we have to compare it to the alpha that's given in the problem. Okay, so remember the 5-step process we did last week? Um, that process is going to be exactly the same. The only difference is that we have a test statistic that has a different equation today. Yep, nothing to do with the z-stat. This hypothesis testing, when you have to select the hypothesis, you just have to sort of read the problem and see what they want you to test, and that's what you select. The test statistic is part B, right, which is the value you get from here. Okay, so you reject the null hypothesis because there's sufficient evidence to conclude that P1 is greater than P2. Why do you have sufficient evidence? Because your p-value is less than alpha. Okay, and that's why you reject the null hypothesis in favor of the alternative hypothesis. Is this clear? Simple, right? The rest of it is very much like last week. If you mastered the concepts and the process last week, it's no different this week. The only difference, again, is the fact that you're using a different test statistic equation. That's it. Okay, now they want you to construct a confidence interval for P1 minus P2. So instead of doing a hypothesis test, now they want you to calculate the confidence interval. And so what I'm going to do is I'm going to erase this. And I'm going to show you how StatCrunch will do this. So again, you have x1, n1, x2, n2, right? I can calculate my p1 hat. I can calculate my p2 hat. Okay, just like we did in the previous problem. I can calculate these two. Now, in order to calculate the confidence interval, what we do is we take the difference of these proportions, we add and subtract the critical z value times this whole thing. Okay, and so for example, in this problem we have, let me just write this down here. We have 383 and 501, and x2 is 407. Now these numbers will be different for you, okay? Every one of us gets a different set of numbers, so so here are the numbers that I have, okay, in my problem. So I have x1, n1, x2, n2. These are the values. Okay, so I can calculate this, and I can calculate this, right? So I can calculate, I will have this, and I will have this, right? And then since I have the P1 hat, I will have this, I will have this. I know my N1, I know the value of it. I have this, I have this, I have this. I have everything. This is the only thing you have to find. But you know how to find it, right? The question says we need 90% confidence interval. So let's see who gets the extra bonus point. tonight. How can we find the critical Z for a 90% confidence interval? Can someone walk me through it? Let's see. It's a pop-up quiz. Okay, not proportion stats. Definitely stat, but not proportion stat. Aha, Amy's got it right. I'm gonna go to calculator and I'm gonna go to normal. Okay, I'm gonna go to normal calculator. Okay, 90% confidence interval. What do I do now? Between. Conrad's got it right. I'm gonna go to between. Okay, 0.90. Very good. I hit compute and I get 1.645 is my critical value. 1.6449 or 1.645. Very good. 1.645 is my critical value. Awesome. Okay. So I have my Z also. It's okay, so it's between because it's a confidence interval. There's a critical value on the left, critical value on the right. When you have 90% confidence interval, the middle region is 90%, right? So you have 5% on the edges. That's why. That's why we went to between. Whenever you have a confidence interval, right, there's a lower limit and an upper limit. That's why. So I have all my values here. I have everything given to me. I can just um, pop in these numbers, okay, in their places and calculate the confidence interval, right? This is a plus and a minus, so I will get a lower limit and an upper limit, okay? So do you all agree I can do this for this problem? I have all the numbers given to me. Everything is given, okay? So now let me show you how StatCrunch will do this. So I'm going to go to stat and I'm going to go to proportion stats. I'm going to go to two sample and width summary. Okay. Same way as I did in the previous problem. I'm going to plug in these numbers 383, 501, and 407 out of 564. And I'm going to go to, instead of performing the hypothesis test, I'm going to choose confidence interval. I'm going to choose 0, 90% confidence interval, so it's 0.90. I hit compute and take a look at what I get. I get the lower limit and I get the upper limit. It's minus 0.001 and 0.0868. Okay, and that is my correct answer. Why did we do both ways? I'm not sure if I understand that question. No, we didn't do it both ways. So these are two different problems, right? That was to calculate the critical Z value, right? This is from week 3. Critical Z value so that I can plug it in this equation and manually find the confidence interval, right? This is a straight up calculation that StatCrunch does to just give you the confidence interval, okay? You don't need to find Z in this case. I hope I didn't, I hope this is clear that this method is the manual method. In the manual method, you have to calculate your Z yourself, right? That's why we went to normal calculator to find our critical Z. But when we go to this two sample proportion option, all you have to do is specify what is your confidence interval, 90%. And what it's doing is when it calculates the lower and the upper limit, it's performing the calculations for this whole equation, including calculating the Z. Okay, so you don't have to do any of this. So I still feel there's a little bit of confusion here about how the difference between calculating the Z, the critical Z, and calculating the confidence intervals themselves, right? these are two different operations. So Erica, I would suggest to check out week 2 webinar recordings. I think that will help out, as to why we do the critical Z calculations and how we do it and how that's different than um, calculating the upper and the lower limit, which is week 3. So this is the difference in week 2 and week 3. And yes, so for manually, if you want to do this manually, you'll have to find your Z. And the only way to find Z is using the normal calculator. If you do it using StatCrunch, then but this I think what I'm trying to maybe say is it cannot be explained easily. You sort of have to actually do these two calculations to see what the difference is. Yeah, of course. I think it's definitely recommended that you use StatCrunch to do all your calculations. And part of the course is that you have to learn a software package because in real life, statistics is done using software. It's not done using manual equations because sometimes your sample sizes are really, really large. You can't really do manual calculations. Um, but as students, if I just show you how to do it in StatCrunch, if I just, I don't tell you the background and I just kind of show you this is how, this is what you have to click to get to the answer, I think I will not be doing a good service. And I think that, you will not appreciate what is it that StatCrunch is actually doing in the background, right? So that's why I do the manual way to show you. I don't actually calculate it, but I just show you that you can calculate it if you wanted to, right? And then, of course, I think you should all try it at least once to match the answers, right? So, okay, so we get our answers, and you can see that this is the correct answer. This is the lower limit, and this is the upper limit. By the way, does anything stand out when I show you this lower and the upper limit? Does anything stand out here? Let me see if someone can pick it. Yeah, but there is a negative sign. Then what is it implying? There's something special about this hypothesis, this confidence interval. Still not what I'm looking for. There's something in here that we talked about last week briefly. Okay, maybe I'll give the answer. The answer is that notice that 0 is included in this interval, right? 0 is a part of this interval because the lower limit is negative 0.001. And so 0 is between these two limits, right? Since 0 is included in this interval, if you were to do a hypothesis test, you would not reject the null hypothesis, right? Because the null hypothesis is essentially included in this interval. Does that make sense? We did this last week, so the same concept applies this week, okay? Yes, every time 0 is included, that is true. Now, sometimes you may get instances where like this is very close, right? This is almost 0. The lower limit is almost 0, right? So in this case, it could go one way or the other. But if 0 is included in the interval, then that means your null hypothesis is included in the interval. You cannot reject it. Okay. All right. Let's go to the next problem, and we go back to hypothesis testing. Okay. So in a clinical trial of a vaccine, 10,000 children were randomly divided into two groups. The subject in group 1. Okay. So there are 10,000 children divided into two groups, 5,000 each. The subject in group 1 were given the vaccine, while subject in group 2 were given a placebo. Placebo is essentially like an inactive form of the vaccine, okay? And individuals don't know what is a placebo and what is a vaccine, okay? So you have 5,000 children in each group. One is an experimental group given the vaccine. One is a control group given a placebo. In the experimental group that's given a vaccine, 78 of the 5,000 developed a certain disease. But in the control group, 109 developed the disease. Okay, so obviously when you give a vaccine, you expect fewer children to develop the disease, right? As compared to the group that gets a placebo. So this makes sense, right? 78 versus 109. But the question is this statistically different, right? They are different, obviously, but is the difference statistically significant or not? That's the question. So we have to do a hypothesis test. So it says determine whether proportions of subjects in the experimental group who contracted the disease is less than proportion in the control group. So if I say experimental group and this is the control group, okay? If I say this is P1, proportion 1, and the control group is proportion 2, and my question is, I have to test whether the proportion in experimental group is less than proportion in the control group. So what would be my null and the alternative hypotheses? So first of all, what would be the null? Yeah, the null is simply P1 equals P2 or P1 minus P2 equals 0. Okay. What would be the alternative? Very good. P1 is less than P2 or P1 minus P2 is less than 0. Okay. Excellent. Excellent. So these are the two hypotheses I'm testing, and you can see that this is the right answer. Null is that P1 equals P2. Alternative is that P1 is less than P2. Okay. Now we have to determine the test statistic. So let's see if you can walk me through this problem. So what I'm going to do is I'm going to clear this and see if you can help me do this problem. So how would I go about it? So the equation, the manual equation will be the same as we did before, so I'm not going to write that out. But yes, so I'm going to go to stat, proportion stats, to sample with summary. Very good. Okay, and then what do I enter here? "78 out of 5,000." And here I'm going to enter 109 out of 5,000. Very good. Okay, and then what do I select here? P1 minus P2 is 0. And what about this alternative? Less than. Yes, very good. And then I hit compute and I get my test statistic and my p-value. So let's look at the p-value. The p-value is 0.0111. Okay, so essentially 0.01. And my alpha is 10%. So what is the conclusion for the test? I reject the null hypothesis, right? I reject the null hypothesis. So what is the conclusion? What is my conclusion in terms of like words? What will I conclude from this test if I reject the null hypothesis? There is sufficient evidence for, well, Conrad, there is sufficient evidence, right? There is sufficient evidence to reject the null hypothesis. Very good. That is what I was looking for. Sandra's explanation is what I was looking for. Since we are rejecting the null hypothesis, we have evidence that P1 is less than P2. If P1 is less than P2, what does that mean? It means that the vaccine is actually doing a good job of, helping out with the disease, because there are fewer children in group 1 who have the disease when they get a vaccine compared to the control group when they don't get the vaccine, right? So there is sufficient evidence that the vaccine is successful. Excellent. Very good. Does that make sense, everyone? Does Sandra's explanation make sense? Yes. Excellent. This is an excellent way to sort of summarize the outcome of the test. So the test statistic is minus 2.29. That's from here. The p-value is 0.011. And we say that we reject the null hypothesis because there's sufficient evidence to conclude that the proportion of subjects in the experimental group who contracted the disease is less than proportion of subjects in the control group at alpha 10%. Okay? Yeah, this is a long, but, and again, I think, unfortunately, they don't really do a good job, I think, of explaining the underlying conclusion, which which you specified. I think that is an important piece to include here, so that you can connect the hypothesis test to like the practical, implication of it, right? Because this is the practical implication, is that the vaccine is successful in reducing the proportion of children who get the disease. That is important to specify in your conclusion, and it doesn't do that. Oh, so there you go. So you probably see this quite often. Anyway, great. Any questions here? I think this is straightforward. If not, I'll move to the next problem. So now we're gonna switch gears a little bit, and let's see what we have here. A researcher wants to show the mean from population 1 is less than mean from population 2 in matched pair data. Okay, so we have what we call matched pair data. So what is matched pair data? It's a kind of a dependent sample. Okay, but here's what it is. So you have some unit, okay? You have some unit or individual, and what you're doing is you have two different what we call treatments. So this is treatment 1 and this is treatment 2, okay? And I think the best way to explain this is to go to the next problem, okay? But I'm going to keep this here so that we can come back to it. But this is what it is. You have a unit and you have two treatments. And what you have to do is you have to compare the treatments. So you have to say, maybe, the average for treatment 1, is it equal to treatment 2? Is your null hypothesis, or if it's not equal, it's your alternative hypothesis, okay? But what you're doing is it's matched pair because your treatments are sort of being applied to the same unit or same individual, okay? An example in this case is the next problem, but we'll go to that, but let's answer this problem first. If the observations from sample 1 are called X and the observations for sample 2 are called Y, okay? So the first sample, say treatment 1, is called X, and treatment 2 is called Y, and then they say, now let's assume that D equals X minus Y, okay? So you take the sample values from the first sample, subtract them from the second sample, okay? Then the null hypothesis is that under the null hypothesis, your mu d equals 0 and the alternative is what? So if this is true, then your null hypothesis is that mu d is 0. And let me show you what that means. So imagine this. Imagine that you have some sample. Let me move this a little bit. Probably should move this guy too. Okay, so imagine that I have some sample value. So say maybe for treatment 1, I get a sample like this. And maybe for treatment 2, I get sample something like this. Okay. So D is just X minus Y. So if I were to calculate my D here, it's just X minus Y. So 12 minus 17 is minus 5. 13 minus 19 is minus 6. 11 minus 15 is minus 4. 17 minus 21 is minus 4. Well, D just signifies difference, right? D is just difference. Difference between the first and the second sample. And D is calculated as X minus Y. So I take each X minus Y, I get that. The reason it's called matched pair is because this is a pair. Okay, let me use a different color. This is a pair. This is a pair. This is a pair. This is a pair. Okay, this is called matched pair design. And the next problem will be a good example of it. Okay, but this is what you have to understand. Whenever you see a matched pair problem, okay. Oh no, Sandra, that's fine. Actually, I would like to explain this in as much detail as possible. So those are good questions. So in a matched pair design, each data, how do I explain this? Each data row, okay, is sort of connected with each other. This is one sort of observation where X is 12 and Y is 17, although they are in two different samples, but there's a connection between them, okay? That's why this is important. That's why this is called a matched pair design. In a matched pair design, you can't just take your X and Y and use the concepts we've used previously to calculate your test statistic. You can't do that because matched pair design is separate from the sampling methods that we've been using so far, like the independent samples that we use in the previous few problems. And the reason is because these data points are connected with each other, okay? And so what you have to do is you have to find your D like this. It's just the difference between X and Y. X minus Y is D. And then when I say mu D equals 0, what that means is you take the average here, average of the differences, okay? Take the average of the differences. So whatever that average comes out to be, I don't know, maybe the average will be, who knows, minus 4.5 in this case, okay? The average is just minus 4.5, say. So then the question is your mu D equal to 0? And then the alternative, it can be one of the three again. That mu D is not 0, mu D is less than 0, mu D is greater than 0, okay? Amy says, so is there anything that maybe I can explain again here? Oh, question 7. Okay. Are we on 7 or are we on 6? Oh, we're on 6. Yeah, don't worry. We'll go through 7. 7 will be easy once we do 6. This is just to sort of explain what a matched pair design is. And then the next problem is a very good example of matched pair design. But essentially this is what's going on. You have two samples, just like any previous problem that we did today, except that in those two samples, each data point is connected with each other. Okay, they mean something, and we'll talk about what they mean, and I'll tell you how they're connected. But they are connected, and then if they are connected, you have to find your d, the difference, like this. Then you take your average difference, and then you have to carry out this hypothesis test. This is all. This is all matched pair design is. Now in this problem, it says a researcher wants to show that the mean from population 1 is less than the mean from population 2 in matched pair data. So you have a matched pair data, mean from population 1 is less than mean from population 2. So which one of these alternative hypotheses am I going to choose? If mean from population 1 is less than mean from population 2, which actually my example fits this problem, you're going to get negative d's here, right? You're going to get all negative d's, just like this. So should I select less than or greater than or not equal to? Difference has to be negative. Excellent. This is the right answer. Very good. Because if x is less than y, I will get negative differences. My average will be negative. And so my mu d to test is that mu d is less than 0. Okay, that's the reason why I choose less than sign here. Okay, the average is just, I just take the average of these d's, right? So it's just a simple average. I mean, I can show you how we can calculate the average. Yep, add all 4 divided by 4. Or I can use Excel to do this. So say I have -6, -5, -6, -4, -4. And how do I do this? So I say equal. There's a function called average in Excel. So I type average, parentheses, and then I have to go to the first cell. I'm gonna hit my shift key and I'm gonna hold the shift key on the keyboard and then just select the range of data. Okay, so I select all these 4. So A1 colon A4, parentheses close. So what it's doing is it's calculating the average of these 4 numbers. So I actually get minus 4.75. So I was off a little bit here. So this is minus 4.75, the average. Does that make sense? That's how I get my average. And you can see it's negative. So I'm testing that it's less than 0. Okay. Okay, so now let's look at this example. This is a very good example of a matched pair data. The following data represents the muzzle velocity in feet per second of shells fired from this gun. For each shell, 2 measurements of velocity were taken using 2 different measuring devices. Okay, so here's what's going on. So I would like you all to sort of appreciate my drawing skills now. By the way, no one told me that my status is still away. Nobody mentioned that. Wow. I forgot to change my status when I signed back in the room. Sorry about that. Okay, so here are my drawing skills. Okay, so you have a shell. All right, so the shell of the gun. So maybe it looks like this. Okay, that's the unit. Shell of the gun is the unit. Okay, and it's being fired. So maybe I'll show like, I don't know. Okay, it's being fired here. Okay, looks like a bullet. Okay, well, it's a bullet. Okay, great. Now, what do we have? We have, for each shell, 2 measurements of velocity were recorded using 2 different measuring devices. So you have 2 different devices, okay? So maybe it's one of those um, I don't know if you've ever seen this, but let's see. Okay. So what it's doing is it's not that, not that, not that. It's measuring. So it's sending out these signals and then receiving the signal back to see how fast the shell is going. Okay. And then the same way you have a second device here. Okay. As long as I don't do a terrible job of explaining, I will find that my drawings are successful. Okay. So in this question, is A the same as X, B the same as Y? Yeah, let's not worry about X and Y. Let's just make sure we understand the problem first, okay? So the problem says you have a shell fired and there are two devices measuring the speed, okay? Here's why this is a good example of matched pair design. Think of the shell as a unit, okay? It's being fired, so it's a unit. And now you have two treatments being applied to it that are trying to measure how fast it's going, okay? So you have treatment 1 and treatment 2. And you can see that at any moment, say at time, maybe the time of the day is say like, um, actually before I do that, let me erase, where's my eraser? I'm gonna erase this. Because I think I can do a pretty good job of explaining everything here. Okay, so yes, Rob, absolutely right. This is matched pair because there are two units, two treatments trying to measure the same bullet at any instance of time, right? So say, for example, the time of the day is 12:02 p.m. Okay, so it's like right in the afternoon. At the specific time, the shell is fired, and at that specific moment, these two devices get a measurement, right? So for example, let's take a look at the data. The first data says 794.3 for A and B. So now they're using A and B. So I'm going to use A and B, okay? So now they're not using X and Y, they're using A and B. So I'm going to use A and B, okay? So I'm going to use A, I'm going to use B. So A says the first measurement is 794.3. B says it's 798.6. Yes, you can have that too. You can use three different devices, but that's a more complex case, and we're not going to consider that. So this is the first measurement. The first measurement, say, was taken at 12:02 p.m. The shell was fired, and the two devices took the measurement. Okay, can you all appreciate why these are connected with each other? Because this is the first measurement when the shell was fired at 12:02 p.m., right? So there is a hypothetical connection between the two, right? So can you all appreciate that? And do you see why now this is a match pair design? This completes the match pair design because you have a shell that's a unit, two treatments are measuring it. The same shell is being measured by two different units. And then when you get these measurements, they're connected with each other, right? Because, right? Because when the shell is fired, that's the only time you can take the measurement. And each time the shell is fired, the measurement is taken. So both these measuring devices measure at the same time. That's why this is connected. And now I can find my D, right? The D is simply just 798.6 minus 794.3. So whatever value that is, let's see what that is. 4.3. Oh, I should have just trusted Sandra. Sorry. Minus 4.3. Sorry. Yes, this should be 794.3. Okay. Minus 798.6. So it should be minus 4.3. I should have really trusted Sandra on this one. So minus 4.3. Okay. And then similarly, the second is 794.6, 799.4. So I'm not going to write out all of them, but maybe I'll write one more. So the next one is 794.6, 798.6. Sorry, 799.4. Okay, so in this case, what's the difference? Minus 4.8. Okay. So do you see how I can do this for all the values, right? I can just, write out the values here, take their differences, find the differences, right? Do you see how I can do that? It's always A minus B. Yep, it's always A minus B. So this D is always A minus B. Any value A minus B, but they have to be connected like this, each row, okay? So do you all agree that at the end of the day, just like I did before, I can find my average of these differences, right? Do you also agree that I can find its standard deviations, right? I can just find my standard deviation and the average, okay? So if I can find these two, then it's a win-win for us because my test statistic for this hypothesis test is going to be simply this. D bar, which is the average of D, divided by standard deviation of D over square root of n, where n is how many observations I have. It's that simple. D bar divided by SD over square root of n. This is the test statistic. It is actually much simpler than the one we did earlier today, right? All you have to find are your D's differences, find its average, standard deviation, and then you have your test statistic. Simple. Let's take a look at it. So here's the data. Okay, this is the data given to you. We have to find, why is this a matched pair data, first of all? It's matched pair because two measurements A and B are taken on the same round, just like I explained. Is there a difference in the measurement of muzzle velocity between device A and B? So basically what they're asking is, are A and B measuring, are the measurements from A and B different or not? Okay. If that's the case, tell me what would be my null and my alternative hypothesis. So the first case, what is my null hypothesis? And I'm going to use mu now, the mean, the average, the mu. So what is my null hypothesis? Very good, Mike. Mu A equals mu B. Okay. Basically what that means is that the averages are the same. Well, okay, hold on. Mu A equals mu B is fine, except we have to use this guy, D. We have to use D, remember? We have to use mu D. We have to express the null and the alternative hypothesis in terms of mu D because this is a matched pair design. So how do I express the null hypothesis in terms of mu D? D equals A minus B. Very good, Sal. Mu D equals 0. That is my null hypothesis. Okay. So let me show you why. If D equals A minus B, I can simply just say mu D equals mu A minus mu B, right? And under the null hypothesis, we said that A and B get the same velocity. A and B are equal, right? A equals B, right? That was our null hypothesis. Well, that if A equals B, then mu A minus mu B is simply just zero. Their averages are zero, right? If they're equal. So mu D equals mu A minus mu B equals zero. So mu D is just zero. Does that make sense? Right? Just like from, I mean, if you followed everything in the previous problem, then you follow this equation. You see that? Mu D equals zero. The previous problem, that's what we said. Under the null hypothesis, mu D is zero. The difference is zero. A minus B difference is zero. Okay, that's the null hypothesis. What is the alternative hypothesis? Yes, it's 100% of the time that's your null hypothesis. Now we are interested in, is there a difference in measurements of muzzle velocity between A and B? All we are interested in, is there a difference? We're not interested whether A is less than B or A is greater than B, just a difference. We're not interested in whether 1 is less than 2 or 2 is less than 1. We are interested whether there's a difference. So it's a two-tailed test, yes. So what would be my alternative hypothesis? How do I write it? Mike has write it correctly, but let's see if mu D not equal to 0. Very good. Excellent. Mu D is not equal to 0. Okay, meaning it's different. It could be less, it could be more, but we just need to look for a difference. So this is what you're looking for. Okay, these are your null and the alternative hypotheses. This is your test statistic. And now let's calculate it. So what I'm going to do is I'm going to open this in StatCrunch. And here it is. If you did want to do it manually, here's one way to do it. When the data opens here, you can go to Data, Compute, and Expression. Okay, Data, Compute, Expression. My expression will be A minus B because that's where the data is. Right? A column has values for A, B column has values for B. So A minus B, I want to calculate A minus B, and I will give this column label, this new column, a label D. That's my difference. So what it does is it calculates the D here. See that? So my D now is A minus B for each row. And remember I said you can find your test statistic using this equation. You have to calculate the average of D and the standard deviation of D. Okay, so this is my D. All I have to do is go to Stat, Summary Stat, Column. I click on D, and I can find my average, which is the mean, and the standard deviation. I hit Compute, and take a look at this. I get my mean, and I get my standard deviation. I get these two. I have this now. I have this. I already have N. I know how many observations are there. So I can easily find the test statistic. Okay, this is the manual method. Well, luckily, you can use StatCrunch to do this. For that, I'm going to go to Stat, and be careful here. We're going to go to T-Stats now. Remember, we're using this problem involves calculation of means, right? Average. Remember, I told you last week, whenever you have an average, you always use the T distribution. You don't use the Z distribution. Okay, so we're going to go to T-Stats now. And you see under T-Stats, we have an option called paired, right? So I'm gonna click on paired. My first sample is A, second sample is B, and take a look at this. Mu D under the null hypothesis equals 0, just like this. Under the alternative, it's not equal to 0, just like this. And that's all you have to do. You just hit compute and you get your test statistic, and again you get your p-value. See, the test statistic is calculated using this equation here. Okay, and you get your associated p-value. Now, what do we have? What is the alpha? Alpha is 1%. The p-value is 10%. P-value is more than alpha. So what's going on? What is the conclusion? Do not reject. Very good. We do not reject the null hypothesis because p-value is more than alpha. If we do not reject the null hypothesis, what does that imply? If we don't reject the null hypothesis, what does it imply about these devices? If we don't reject the null hypothesis, nope, Brian. If we don't reject the null hypothesis, what does it imply? D equals A minus B. If the null hypothesis is that the average difference is 0, what does that imply? Sarah, we're not gonna, okay, so we are not rejecting the null hypothesis. So obviously we are accepting the null hypothesis in a way, right? So we can't accept null and alternative, right? We can only accept one. So we are sort of not rejecting the null hypothesis. Yes, so everyone is right, but I'm looking for that implication that Sandra mentioned in the previous problem. What does mu d equal to 0, null hypothesis, not being rejected, imply about the two devices that's measuring the velocity? Okay, so let me tell you what that would imply. So we know our D is A minus B, okay? Measurements of A minus measurement of B is our difference. Under the null hypothesis, the average difference we said is 0. If the average difference is 0, it means whatever values of A and B are, they're equal. If A and B are equal, then your difference will be 0. And we said that we cannot reject the null hypothesis. So we are sort of accepting this piece here. Okay? We should never say we are accepting the null hypothesis, but I'm saying it just so that we, just for the sake of this problem. We should always say that we are not rejecting the null hypothesis. Now, if that's the case, then what this means, what it implies is that the two devices are basically getting the same measurements of the velocity. That's the implication. So I think someone said this. There is not a significant difference in velocity between the two devices. Amy, you're almost there. The only thing to add there is that there's no significant difference in the measurements of velocity from the two devices. That's what I would say. Okay. Sandra is also correct. Very good. That's what that implies. Does that make sense? Does this make sense now? The implication under the null hypothesis not being rejected is that your difference between the measurements A and B are 0. Yes, and Brian took it one step further. We are within the margin of error. Okay, now what they want you to do now is calculate the 99% confidence interval. So let's take a look at that. So all you have to do is go back to options and edit. Instead of carrying out the hypothesis test, click on confidence interval. And I want 99%, so I'm going to put 0.99. Hit compute, and I get my lower limit, and I get my upper limit. Now, do you notice the 0 is included here? You notice how 0 is within these two limits, between these two limits, right? And do you see now the connection? The null hypothesis is included in the interval. And so in the previous part, you did not reject the null hypothesis, right? Well, you didn't because it's included in that interval, confidence interval. Okay, that's how you calculate the confidence interval. And then what is the interpretation of the results? Well, you are 99% confident about this confidence interval. You are 99% confident that the mean difference in measurement lies within the interval found above. Okay. Obviously, remember I said these can be interpreted as the believable values. This is the least believable value. This is the maximum believable value. And what you say is that the mean difference in measurement lies within this interval. Whatever differences you're going to get, they will be between these two limits. Does this make sense? That's how you do a matched pair design. Okay. Now let's do one more problem and then we'll go. A researcher studies clarity at the same location in the lake on different dates over the course of a year and repeats the measurements on the same dates 5 years later. Okay, so what's happening is there are 6 observations. Okay, there are 6 observations. Here are the dates: January the 25th, March 19th. Okay, here is the initial observation. Okay, so on January 25th, say in year 2010, this was the first observation taken. And then after 5 years, on the same day, they took this observation. Okay, same lake, same point. So what should you be imagining right now? You should be imagining my drawing there. Unit, treatment, treatment 1, treatment 2. Boom, boom. What is the unit in my case? What is the unit in this problem? No, 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 no. The unit is the lake, right? The lake is my unit. Okay, lake is the unit. You can say clarity too, lake clarity. Okay, let's say lake water or lake clarity. Yes, yes. So, but basically you know what I'm measuring. So we can say lake or clarity. Okay, and what are my treatments? How am I doing this? So I have measurements. This is the first measurement taken year 1. Measurements. Okay, year 2. Year 2 measurement. These are my 2 treatments. Same unit, 2 treatments. Do you see how this is matched pair? And you can see, since I have time, I'm using the same days because I want the 2 to be sort of connected so that because on January 25th, most likely the environment is sort of like the same, right? And the conditions are pretty much like the same, and that's why they're doing it on the specific day after 5 years. Okay, so this makes it match pair. Why is it important to take measurements on the same date? Because using the same date makes the second sample dependent on the first, and it also makes it matched pair. Does the evidence suggest that the clarity of the lake is improving? Okay, so this is important. What I'm going to say is, I'm going to say initial measurement is A, and after 5 years is B. Okay, and again, my D is A minus B. Okay, now I want you to be careful here this is the only piece that's tricky in this problem. So the researcher wants to know if the water clarity has improved. And the way they're measuring that is they're immersing a disc painted black and white into the water until they cannot see it. Okay, so they immerse it, and until they can't see it, that's the depth. right? That's the clarity depth. And what they want to know is clarity improving? Okay, has the clarity improved after 5 years? If it has improved, would you expect the numbers after 5 years to be higher or lower than the initial numbers? Yes. So if the clarity has improved, you expect the disk to be immersed further down, being visible, right? And so if that's the case, then the after 5 years numbers will be higher, meaning that B will be higher than A. You should get B higher than A. If I define my D like this, A minus B, what is my null hypothesis and what is my alternative hypothesis? And this I want you to express in terms of mu D. So what is the null hypothesis in terms of mu D? Mu D is 0. Now, if clarity has improved, what is my mu D? Gotta be careful. B is more. B numbers are higher than A. If B is higher than A, my mu D will be, yes, less than 0. See, this is the tricky piece. If B is higher than A minus B, this whole thing will be a negative number, right? If B numbers are larger than A, then A minus B will be negative. So D will be less than 0. So that's why mu D is less than 0. Okay, so that's my null and the alternative. Now let's take a look at what do we get for this. So I'm going to open this in StatCrunch, and just like the way I did it before, I'm going to go to stat, tstats, paired. Sample 1 is initial, sample 2 is after 5 years. I want less than 0. I get my tstat, I get my p-value. P-value is 0.3529. So alpha is 0.05. So what do? Alpha is 0.05, p-value is 0.3529. So what is the conclusion? Aha, looks like Conray is tired. We do not reject, right? Because, um, well, we should never say accept, just say do not reject the null hypothesis, okay? We do not reject the null hypothesis because your p-value is more than alpha. 0.35 is greater than 0.01. Do not reject the null hypothesis. I didn't group by anything. There's no grouping. I left the group by just like that. So no groupings, nothing. Okay. I get 0.3529. I do not reject the null hypothesis. Okay. And we'll stop here. And then from tomorrow, we'll get started with, take a look at that, height of father and son. Haha. No wonder I thought of that example earlier. So this is not going to be a matched pair now. But well, this will be a dependent sample. Okay, purely dependent sample. But we'll see how we're going to do this. So we'll do this tomorrow. Okay, so the first 8 problems are done. And I'm going to close this. I will post a recording within the next half hour. So I hope this was helpful. I hope I didn't confuse you more than perhaps you were confused earlier. Ah, Sandra, it's a little too late for that, but that's a very good reminder. Could you remind me tomorrow perhaps? Or maybe next week will be week 6. Let's do it next week, Tuesday. But remind me tomorrow. If we have time, then we'll do it tomorrow. This was a hard one, wasn't it? Yeah, this was a little hard. I think it's I think these are challenging concepts tonight. How do you know which StackCrunch function to use? Practice. That's the only thing I can say. The more you practice, the better you'll get at solving the problems. You do know that once you have submitted the homework and the week is over and you get your grade and everything, you can go back and practice that homework over and over again and you won't lose points. So if you go back after the due date and you try to do the homework again, it will ask you, my stat lab will ask you, do you want to practice or do you want to redo the problems? You can say practice, and then it's just like a practice session. You can keep doing these problems over and over again. Okay, let me stop the recording.